Okay, good morning. So, first thing is about our homework. Okay, this program assignment actually was designed by our TA. So some particular data, some student just asked me about the particular data sets, particular numbers, and particular support thresholds. I think for these questions, you probably should discuss with TA because I myself never run this program, never run this data sets. So I cannot tell you exactly the number. So the best is you either discuss TA during their office hours or you put the question in Piazza if it's commonly interested question. Okay. Then you should be able to get answer quite quickly. Hopefully you will be able to resolve a particular problem. Okay. So since this is a program assignment, I should let everybody know you really should start early. We got lots of students already made very good progress. If you start late, final a few days, you will not be able to handle. Okay. So of course, some principal things you can discuss with me. But for the very concrete numbers, or thresholds or something, you really should discuss with TA. Okay. For the exam questions, I actually prepare some standard answer, but I will not go over at the beginning of the lecture. Okay, that means near closer to the lecture, I probably show you. And see whether you have some common questions you want to discuss and how to do it. We probably can go over it with your requests. That means I actually would like to see you may raise questions, say you still get puzzled on particular questions and answers, then we can discuss. Okay. So we were still first working on our course contents. The major course contents. Okay. Last time we discussed the decision tree induction, okay, which is a very popular method. We said essentially is you need to work out based on the entropy computation, you work out the information gain, which is a typical formula. That means if you pick this attribute as the splitting attribute, you want to, based on this one, to make decisions, there are several competitors. Okay, you pick up attribute A based on if this one will lead you to the best, the highest information gain. You pick it up, then you split it, the tree into several branches. In the meantime, you split the data as well. Okay. Then based on this split data sets, you calculate the information gain again. You decide which attribute will be the second most important one. Then you take this attribute, split it again, you construct a tree. Okay, that's the decision tree induction algorithm. And we also said there are lots of different ways to calculate. For example, you can use split info, you can use Gini index. You actually have many other things we already said. There are many measures used to do decision tree induction. Okay. The information gain, just the first one, probably the most popular one. People just use this as a textbook material. Okay. Then we may get into problem is you use this decision tree induction method recursively. You construct a tree. And the tree can go very deep. Okay. But if you do this, you may get into overfitting problem because finally you decide your splitting is based on very small set of your training data. Okay. The set is so small, it may not be very reliable. Okay. So when you do the splitting, the remaining part of splitting may only fit your current training data well. Okay. But when you get a different kind of data coming in to test, to really use, you may make mistakes because their decision could be wrong. based on so small set of data. So that means you got an overfitting problem when the tree goes quite deep. So to avoid this overfitting problem, there are several ways. Okay. Most people call this is tree pruning method. But for tree pruning, there are two kinds of pruning. One we call pre-pruning. Pre-pruning means while you get into this tree, suppose this site, the data sets, is reasonably uniform, or it is, pretty small data sets. You probably say, I don't split anymore because the data set is so small. When I split it, unlikely it will give me very reliable answer when I got the unseen, the new data, okay, coming in. In that sense, you halt the tree construction. That means you do not split this node anymore. Okay? And what about this node is still not pure? Okay? Of course, it's pure. You don't have to split. Okay? If it's not pure, in most cases, you take the majority. You can say, because the majority of people say this one is positive, then you will say it's positive. Okay? Of course, you will make some error, prediction, but suppose the error is acceptable. Okay? Then you just halt this. We call this is pre-pruning because you don't split anymore. Okay? Another way is post-pruning. Post-pruning means you construct a tree. Okay? Then you take the test data, or we call, say, validation test data. It means you take those data, you already know the label, but you just do not put them into your training process. Okay? In that sense, you take those validation data, you go inside to see whether you will make a right mistake or wrong mistake. Okay? You make things right or wrong. Okay? If you make a mistake in your pruning by going deep into the tree, okay, you will say that part of branch, it's not good, or chop it. Okay? That means you remove some branch from a full-growing tree, and you prune the tree, that part of branch. Okay? That one we call post-pruning. It means you use validation set to prune your tree. Okay? So that's a typical two ways to handle overfitting problem. Okay? Of course, you may say whether this is the best way. I should say, if you only want to construct one tree, this is probably the best way to do it. Okay? But in reality, there are lots of people doing, for example, they do random forest. They construct many trees, finally ask those trees to vote. That probably give you better results rather than you just rely on one tree. Okay? But here, just say, suppose you want to construct one tree, you have to overcome the overfitting problem. You have to either do pre-pruning or post-pruning. Okay. Now we come down to another problem is, what about your training data? It is really, really huge. Okay. Remember, in most machine learning studies, you say, I give you some training set. The training data is not big. Okay. Not big in the sense, for example, you got some tissues. You say whether this contains cancer cells or this is no cancer. Okay. So usually you will not get a very large number of tissues. You get a few tissues the experts may label it. Say this is cancerous, this is benign. Okay. So that's fine. The data set is pretty small. The training data is small. But in some commercial applications, like nowadays we are in the internet time, okay, you got lots of records. For example, you go to Amazon.com, you will see millions of people buying things. Okay. If you say those kind of things, people buy, people click the button or buy, you'll find the data sets is in the order of minutes. You really know they buy or they don't buy. In that case, you may really have millions of training data. You can think about Walmart. They put certain ads to see, whether those customers will buy or not. You probably will see it also in the millions of customers. You can construct your decision tree or something. Okay. You get such huge data sets. They all have labels. Okay. Of course, you still want to construct a good tree or good classification model. You get a new customer coming in, you probably want to say whether I should promote these ads or not promote it. You have not many, millions of training data. If you base on the previous methods, there's one problem is you even have to fetch your data from the hard drive to the main memory many times back and forth, because every time when you want to calculate something, suppose you have 20 attributes. You want to see which one put on top. Even to construct one tree, you first compute this attribute. You say, no, this attribute may not be that good. And you bring another attribute in. Remember, every time you bring your table is so big, it just cannot fit in the main memory. Then you have to swap them back and forth again. That wastes a lot of time. Okay. Then people are studying if your data set's really big, it just cannot fit in your main memory, how we should do, say, decision tree induction or any other learning methods. Okay. So people actually in the database community, once they study data mining problem, they know, in the database, you want to access a huge amount of data. They have lots of tricks. They do indexing. They have lots of tricks how to fetch things to the main memory, reduce number of scans. And those other people, they develop quite a bunch of algorithms. One interesting method, actually called rainforest, developed by Johannes Gurk, Raghu Ramakrishnan, and Ganti. Okay, these three, they published in 1998 in the database conference. Actually, Johannes, after this, I think it just over 1 or 2 years later, he got his PhD. He became a professor in Cornell University. So that's Raghu Ramakrishnan was in Wisconsin at that time. Johannes Gurk actually went to Cornell. He actually interviewed here. We gave him an offer, but he finally decided to go to Cornell. Later, I actually invited him back to give a talk about his new work. But now he actually joined Microsoft. But anyway, let's look at what he did. He did is that actually the thing become why he published this algorithm. That means no matter how big your training data is, how small your main memory is, actually you can, for any time you decide one splitting, you just need to scan the data, the whole data once, no matter how big it is. Let's see how he can handle this. Let's take this one. This, of course, is very small. It's only 14 objects. Okay. But you may think this is 14 billion objects, right? You can think that way. And you only have a small laptop. You want to do decision tree induction. You want to get there. How can you make it, using your tiny memory handle huge amount of data? Actually, what he did is pretty interesting, pretty simple. You can think of this. You scan database only once. Okay, that means you take every tuple, put them into memory only once in your whole decision in comparing all the attributes. How can you do it? Okay. He designed a tiny table. This table called ABC list or ABC set. What is ABC? A is attribute. Okay. B is value. C is count. Okay. This ABC means attribute, value, count. What do you need? You scan database once. For every possible attribute you want to examine. Suppose you have 20 attributes. What you need is just build this one. Okay. Build this table in your memory. How big you need? You think about no matter how many billion objects you have. When you split the data, for every attribute, you just needed this one table. Okay. Then for every possible splitting value, for example, this one has 3, you just need 3 slots. This one has 2, you need 2 slots. This one has 2, you need 2 slots. Okay. And how many label this value you need? If you say you are doing binary, yes or no, that means you have only 2 labels, yes or no, you need the 2 slots. That's all the memory you need. You think how he did it? Okay, it's pretty simple. What he did is this. You scan the first one. You say this is less than 30 age. This is high income. This is student is no. Credit rating is fair. The buying computer is no. How you do this? You just say here, this one is less than 30. Okay. Less than 30, buying computer is no. And here, you just say less than 30, no is 1. Okay. Then later you get another less 30, you'll get another no. The no becomes 2. Okay. That means what you did is you attach each attribute value just to count how many yes or how many no. Okay. You put it in. That's all you need. Okay. That means when you scan through the whole data sets, you fill in those counts for every attribute, their value label combination. You fill in the count. Okay. Why you do this? Okay. You think about it, how you calculate your information gain. Okay. You go back to your formula, you look at your information gain, you probably know this is all you need. Okay. Why? You can think about it. You have a few competitive attributes. Suppose now you have 4 competitive attributes. You will know which attribute to give you the best information gain, right? That's what you want. And you look at the information gain formula. What they need is just this labor distribution. For each value, their labor distribution. That's all you need. Okay. Actually, it's almost anything you need, not only for decision tree for information gain. It is for anything, you just need those values. Okay. If you look at this formula, okay, the formula said you need a log. This is P. P. What is P? P is probability. What is probability? The probability means for this particular labor, okay, or this particular attribute value on this labor, what is the probability to get yes? What is the probability to get no? Okay. If you get a total 9 values, you get 5 is yes, 4 is no. What you need is just 5 and 4. Okay, that's all. So that's once you go inside formula, look at it. Okay, actually not just information gain. You go to Gini index. You look at this. Okay, look at Gini index. This is just probability. It's still, on particular value. Okay, this is the particular value splitting, and what is chance to get yes? What is chance to get no? Okay, so. Actually, you go to any formula on decision tree. Later, you even see, you do naive Bayes. You get any formula like this. What you need is just this value. Okay, that means if you go back and read all these numbers, actually it's very simple. What you need is just say every possible attribute, every possible value, what are their labor distribution? Okay, that's all you need. That's why it's very smart. You just say, no matter how big the data set is, this table is very tiny. You think about it. You get 20 attributes, you get these 20 small tables. Each table, you have 3 splitting points, you just 3 slots. You have 2 labels, 3 times 2 is 6. You just need the 6 slots. And all these just counts, right? How big? It's just the integer or double or whatever. You just need some very small number. So what he says is, in the main memory, before I calculate any information gain, what I need is you scan data once, you count all these things you put into this table, and then you can calculate. Suppose now you say, I want information gain. Okay, you use this thing, you can calculate information gain. You say, I need a Gini index. I calculate this, I give you a Gini index. So it's very simple. This is for one split of the tree. Okay, you think about it because your table is not splitting yet. Okay, you calculate this. What about I decide suppose I take age as the top of the tree, I split this into 3. Okay. Less than 30, 30 to 40, over 40, I split into 3. My table here is also split into 3. You think about this. Because based on the age, essentially sort on the age. Age less than 30, get one table. 31 to 40, get another table. Over 40, get a third one. Or you can think that this table itself was sorted somehow. Okay, but in a very large database, you don't want to sort tables. You just put them into smaller ones. Okay. Then for this, when you scan the second time, you can keep this one again. That means essentially you build another smaller set. Okay. Later, I probably in the final exam I will ask you how much memory you totally need for the first layer of tray, second layer of tray, or third layer. You can calculate this. I'll tell you what is final exam question. Right? But you can see this actually is very simple. You do not need much, right? You can see there's how many slots you need. It's very tiny. Okay. I mean, I don't say 100 bytes, but at least 1 kilobytes per can fit all these in, right? It's a very tiny memory. Then you don't need much. No matter how big this data set is, what you really need to put in the memory just like a kilobytes or less than kilobytes, right? So then you can do all the decision, do all the computation, decide where you want, which attribute you want to pick, how they want to select. Is that clear? That's one of the chapters of his PhD thesis, right? But it's a nice idea, and the first people found it. Okay, of course, once the researcher found it, I can teach to anybody in 5 minutes, right? So then you don't need a lot of memory and a lot of scan. You just need this table. That's it. Okay. Actually, this one can be used for 9 days, for many other things. No matter how big your training data set, you needed just something like this. Okay. So this one is a rainforest. It's a very interesting method. Just give a nice name. Okay. So that means you just need this ABC list. Okay. That's all things you need. You get a few ABC sets. Then you put everything in the memory like that. The remaining thing, getting a page in, you calculate this. Get another page in, you calculate this. How many pages you finally just need this. This one, I believe, is less than a page. Okay, so that's about a scalable process. Actually, you can see if you construct a tree, you can easily to visualize the tree. Okay, this one essentially is saying, originally, you suppose you have 3 classes. Your root part have this distribution. When you do the decision tree induction, you may get something only one uniform, very pure data sets like this. Okay, you say, oh, this one is just one class. Okay, then you may say you can further split it to get other things. Okay. This is just to show you the tree can be visualized. You can easily see how nice the tree is. Of course, a nice tree means the tree is not so deep. At the end, almost everything is in one class. Either it is blue, or it's green, or it's red. It's like a reasonably pure. That means you really can make nice things. Right? So that's a decision tree presentation. This one actually was, I think, the SGI's mindset. That's a software at that time by Silicon Graphics. They are very good on graphics. Of course, I think Silicon Graphics now is non-existent. That time was, I think it's a Google or some Facebook took Silicon Graphics. I think it's a Google took the Silicon Graphics site. So you go to Google site, actually, you ask them the history, this building belongs to the other company. Okay. And that one was, you can see, they just show you, this is the root. There are 4 class distributions. But if you make a decision tree, actually they can use those Dolly to go very, very deep. You can see the tree, some tree it's only one class, so they make the visualization look quite fancy. Those are decision trees. Of course, you don't want to construct a tree too big. Okay? That's already quite fancy, quite deep tree. In most cases, the tree is not that big. Okay. That's visualization. there's another interesting thing is there's one group in University of Munich, Germany. What they did is they say, of course you can make decisions based on information gain, based on Gini index. What about you map this tree in some way in a visualized form, okay? Then you can look at this one. You probably will know where to split is better. Okay? You probably can see this. This is the one. There's some interesting story I can tell is this. I went to, that time I was in Canada. There were some people from Alberta. Okay? You know, Alberta got lots of oil. Okay? They are oil company. They want to make decisions on many things. Okay? Remember, now you probably know there are lots of oil is not from you dig a hole, the oil will spray up. Okay? Actually, in Alberta, their oil is they dig out the sand. It's oil sand. The sand is soaked with oil. Okay? You dig a sand, then you put it into certain big stove or something. You put some chemical, put some heating, then the oil will split. Okay, you will get some oil out. Okay, then you have to treat but you know these sometimes environmental is not so friendly because you put those chemicals, the chemical will, if you put too much, essentially dump it into the field, you know, the crop cannot grow. Okay. So they have to try to reduce the chemical and reduce the heat and produce better oil. But different kind of oil sand actually need a very different decision to make to get the maximum oil out using least energy and the least chemical. Okay, so that's the decision-making process. What they do is they have lots of experts. They know how to do it, but different kind of oil sand, actually they need it very tricky. They total have like 40 different parameters. They need to adjust where to make decision to cut. So this one just shows in that situation, if you just use all the analytical methods, sometimes it's very messy. Okay. But if people watch it, sometimes they know where to cut. Why? You can think about this. Each the sector, each eye, is one parameter. Okay. Then that different decision actually were different class with different color. Then you probably can see what you want to pick up as a good decision is something reasonably clean. You can see these are very messy. That simply says using those parameters doesn't make any sense because you sort them, the different class are scattered inside. Okay. Of course, this is sorted and combined. You look at this, it's very messy. You don't want to use it. You watch something reasonably clean. Like this part is clean, this part is reasonably clean. You take this as a first splitter. That means when you choose attribute, you want to choose something reasonably good. They use different values. You can get a clean result. Like this one is brown. This is brown. This is like blue or something. You think you can make a good splitter. In that sense, you pick this one. This is the attribute. These are the splitting points. Okay. That means it's more like you think about it. You take H. You can say this is less than 30. This is 30 to 40 or something like that. You make it reasonably nice. So actually what they say is, of course, the numerical data can give you something. You can use information gain. But something is quite blind. Okay. What they say is, if I can map them into this pie, you watch it, you know which one is better. The cleaner, the better. Okay. So you can pick up like this one. You pick up it, you say, I almost can cut it, I can make a reasonable decision. Then I get another pie, I can cut it again. That means the wire is split, I get another pie like this. What you need is several layers, you need several pies, and people watch it. Okay. This actually is what he called this is a high anchor. Okay. what he calls interactive visual mining to do classification, to do like this. That's a visual classification. That's what he did in his thesis. It's pretty nice. People can see they actually try to compete with, by human eye, to compete with the decision tree information gain computation. Okay, so that shows, if you understand the principle, you have many games to play. So now we finished the first method, decision tree induction. Now we come down to another method called Bayes classification method. Okay. Bayes classification method, in many typical machine learning textbooks, they actually put this one as the first one. Okay. Why they put this one as first one? Because this has a nice statistic foundation. Okay. What is statistic foundation? That basically based on Bayes algorithm, Bayes theorem. Okay. That means that the typical statistics, you have the conditional probability. You just based on the conditional probability, you can work out these formulas. Okay. And this one is kind of theoretical foundation. A lot of classification methods just based on these statistic foundation. No matter you do probability graphic model, you do a lot of fancy models, the basic statistics is still Bayes. Okay. So that's why they think it's a very foundational. And based on this, they work out a very simple Bayesian classifier called naive Bayesian classifier. We are going to introduce this naive Bayesian classifier. But this one even is very simple. You made a very bold assumption, but still get a reasonable performance. And people actually try to say that this performance is not bad. Okay. And then another thing is you can do incremental. You add new data, you just adjust your Bayesian statistics a little. Okay. Then you actually can. That means originally you say there are, this condition, there are 4, positive, 5 negative. You add a little more, you say now it's become 5 negative, 6 positive. So you add a little condition. So it's very easy to do incremental. Another one is because this one is theoretically is pretty elegant and nice. Usually when other algorithms, they try to explain it, they're actually going back to this basic statistics to explain it. So if we understand this essentially just a Bayes theorem. Okay, you just change the formula a little. Okay. If you think of this is the total probability, okay, the probability means you get a probability on B, you partition them into different conditions. Okay. Suppose you have 3 conditions on A. Okay, like age, you get 3 different age groups. Then for each one, you can get their probability, right? You add together, you get total probability. Okay. Then you can, based on this, you can change the formula a little. You can use this conditional probability to calculate this. This essentially is a Bayes theorem. You just change a little, you get into this computation. Okay. This computation, essentially, most people call this probability on this particular variables. This x is just a vector of the variable. Okay. And they call this one is data sample or evidence. Okay. And this H, you can think is a hypothesis. That means the hypothesis could be this sample, this X belongs to class C. Okay, so this is the hypothesis. And then you get a conditional probability. You say, give me a data set, or you can say a vector X. What's the probability is in this class C? Okay. So that one we call is posterior probability. That means you give me this X, I get the probability in which class. It's like I made a decision already. Okay, that's one called posterior probability. And the initial hypothesis, without any condition, this one called prior probability. Okay. Then essentially you want to compute this, you need this probability. That means under this hypothesis, what's the chance I will get my data, fit into this one? What's the chance to get this data? It's a likelihood. Okay. So essentially, this probability formula, they just give a little nice name is this. I just rewrite this formula here. Okay, copy down here. This one, they just write it in the English term says the posterior probability. Posterior means you give me the set, I really tell you what the chance to get this seat, get this class. This posterior probability actually is equal to this formula. This formula essentially is, this is the likelihood, this is the prior. Prior means actually, I just get a whole data, what's the probability is cancerous, what's the probability is benign. I do not look at your particular sample. Okay? So this is the likelihood. Okay? Then this is your prior, and this is your evidence. So they change this formula essentially conceptually. They say how to calculate posterior probability is you use likelihood times prior divided by evidence. Okay, that essentially is just English interpretation of this Bayes theorem. Okay. Now, the key becomes how can we calculate all this probability we can get a nice answer. Okay. So the major thing, if you think about it, you say, oh, this, like every time I can calculate the posterior probability based on this. The problem is so simple. Problem is, actually, you need all these probability to calculate one probability. But all these probability may not be available. Okay, so that means if you want to compute this, you may need to compute many other probabilities. Finally, you compute this. Then we will see in reality how we do it. So we still just to say how we should do classification is suppose you have M class labels. Of course, in most cases, you only, if it's binary, you only have two classes. Suppose we have M classes. Okay? That means you can put into any one of these M. Now you get n-dimension vector. That's your data sets. You have n-dimension x1, x2, xn. That's your data set. Okay. Then, based on this theorem, basically the idea is you calculate this probability. That means you want to calculate the posterior probability. You need to know this likelihood. You need to know prior. You need to know evidence. Okay. Then you know all these probabilities. You can calculate the posterior probability. And how do you do classification? Classification means suppose you have C1 to Cm, M classes. Of course, in most cases we discuss, we just say two classes, positive or negative. Okay. So this one, this C sub I means you compute the chance to get positive or chance to get negative. Or if it's M classes, means what's the probability for this particular data? It's classified to C1, C sub 1, C sub 2, to C sub N. So what is the final classification you want to make? Is you calculate which one get a maximum one. Okay. The maximum one is the winner, is the class. You think about it, it's more like you do the presidential election. Okay. Suppose now we have 4 candidates. So what's the chance, Trump will win? What's the chance Hillary will win? What's the chance, the other two will win? You based on this, you calculate the highest probability of the winner. Okay. So that's the same kind of thing, right? If you think in this essentially doing classification is finding the highest probability. Okay, that's a win. Okay. So that's they call maximize or maximum posterior probability is the class you want to claim. Okay. Now we got into naive Bayes classifier. Because the real classifier, the full, using this full Bayes algorithm, is you have to know a lot of probability. But that's very hard. But then the people say, what about we assume every attribute are independent? Because remember, you have so many different attributes. You have x1, x2, to xn. These attributes, in reality, they may or may not be independent. Okay, just thinking about this. When you think about it, you have age and income, on whether they are student or like those you try to decide buying computers, but they are not quite independent. The age and whether they are student actually somehow related. You say this guy is 80, you will not believe this guy is a student. Right? If this guy is less than 10, probably still not student. You assume it's student. Right? So they are not quite independent. But if you have a simple assumption, you say the independence, I can allow it. Or I assume they are really independent. For example, you say whether this guy is rich or not is probably not purely depending on the age. Then you can say this, whether the income or credit rating or age are independent. If you make these independent assumptions, that means, those attributes, they are mutually exclusive or they are independent. Okay. Then you can actually thinking about this x1, x2, xn based on their individual attribute. You actually can make them somehow like that means this class under this class Ci, whether it's x1, or whether it's x2, these several attributes, you can split them. You don't have to tie them up. Once you split them, you can say, I can make all these just one factor. I can multiply them together. Okay. So that's the case. You can say, I make a simple assumption. If they are all conditionally independent, the formula becomes simpler. They just multiply all the independent deciding these this first attribute, like age, like income, like whether they are students or not, is completely independent each other. Okay. Then you can just make the probability multiplying together. That kind of classifier we call a naive base. Why we call it naive? Because you assume every attribute is independent. That's pretty naive. Naive means you assume their student or not is independent of age or independent of the credit rating. Sometimes it's a little naive, right? Because you know the age and the student are somewhat, have some kind of relation. Right? So if it makes this assumption, you reduce the computation cost. Of course, you make things more approximate. Okay? And then you can calculate it easily. How easy you can calculate? If this A is categorical value, for example, student or non-student, that's very easy. Then what you calculate is just based on number of tuples divided by the whole thing. Okay, then you get the probability. So it's very easy. That means you, based on this one, you take this attribute value, okay, you divide by the number of tuples. This one is in the whole data set. So you get a probability. So it's very easy. What about a continuous value? Okay. Of course, so even we do the age, we do not do it continuous. We just partition 3. Less than 30, 31 to 40, and greater than 40. Okay. But suppose you say, I'm not going to do that. I take every age, every year into the count. Okay. Then what you do is you assume this one is a continuous value. Then what you can calculate is you just use Gaussian formula. The probability, whether it's this value or not. Because the real value, for example, you just assume the student, you get all the distribution except that you find this group of students, they don't have an age 26. Of course, probability-wise, you do have 26. But you can say they're 25, 27, 28, and they're 23, 22. You, based on this, you can calculate this, right? You can calculate based on the Gaussian distribution, you will calculate what you get 26. So you will not include 26. So in that sense, if it's continuous value, use Gaussian. Okay? Then you can just change the formula. Literally, you still can So that's the naive Bayes classification. How good is the naive Bayes? Actually, it's interesting is people actually even tried it in a reasonably competitive task. After you remove some obviously dependent attributes. For example, if you take birth year and age, those definitely are they are not immutable. You based on a simple formula, you can get a birth year and age you can calculate, right? Just based on the current year. So those attributes you have to remove. That means you first look at their strongly correlated attributes, remove them, then you use naive Bayes. Actually, it's not bad. The final result is pretty competitive. Of course, there are stronger methods, like you can use random forest. You can use many other methods, like support vector. You may get better result. Actually, it's very interesting. I remember there was one statistician in University of Wisconsin came here to give a talk in this room. He did like 72 or something. It's closer to 100 measures on all these different things, including naive Bayes, including distinct tree, including many advanced methods. He did all these tests on different data sets. He finally said there's no clear winner. The simplest method, like naive Bayes or decision tree, and a very complex method on different kinds of data sets, you even cannot clearly tell the clear winner. That time, I think it's about 10 years ago. Of course, now you probably know there's something like deep learning. They really claim they are a big winner. Okay, so that could change the history. But in that time, actually, they say he actually claimed he studied so many different methods, and there's no absolute winner you can claim. That's why people still use those very simple methods, like naive Bayes. Plus, naive Bayes and the decision tree, they are very easy to explain. We explain to like physicians why you make this decision. Actually, they buy it because it's so simple. They can see this is important factor. This is another important feature. How they combine together, they make a decision. Right? So they based on their practice, they probably will buy it. Okay. So let's look at this naive Bayes, how we do it, okay. How the whole thing was running. We still take the same data sets. We still say there are only two classes, buying computer, yes or no. Okay. Then we want to see, now I give you a test set. I say now the age is less than 30, and income is medium, student is yes, credit rating is fair. I want to see what's the chance you will claim it's buy computer or not buy computer. Okay. Then you can see how the naive Bayes is doing. Okay. Actually, it's pretty simple. What you do is you, based on the previous formula, you assume everything is independent. Since they are independent, you can compute their independent probability, right? You can see, you based on this data sets, you can easily compute this probability. Buying computer is yes, what's the chance is less than 30. You just count this. You say yes, okay, buying computer is yes, then what's the chance is 30, less than 30. You can easily calculate, you total have 9 tuples buying computer, the chance to be less than 30 is only 2. So you can figure this one. They do not buy computer, you have 5 such tuples. That's less than 30 actually is 3. So then you can calculate this probability. Right? Then you can calculate all the other probabilities. Like if yes or no, remember this is medium, you can get a buying computer yes or no. I just told you this random forest. You can think about this computation, this whole formula. You can easily get it from random forest, that small table, right? ABC set. You take ABC set, this almost there already, right? Very easy. That's why Johannes Gurkov invented it or discovered this ABC set. Here is magic. You don't need actually any computation. You pick up from the ABC set and put it in. You get the formula already. Right? You can get this. Okay. Then you can see here, this your ABC set also can get the total one. This is your trial. Okay. And then you actually can get, you compute this, You just say, Buying computer, this is your prior, this is your whole thing, you multiply them together. Okay? And then not buying computer, this one. So you finally, just based on these formula, you can calculate this. You will see which one is higher. Okay? Obviously, the buying computer is higher. Okay? Then you're done. Okay? You can see you basically based on the formula like this. This is the 90 base formula. This is the whole thing. This one you times this prior. Actually, you time this one out, it probably, But finally, you can get this one 0.028. This is so low. So in that case, you can say buying computer. So this essentially is just calculate every probability independently. You multiply them together. This is just multiply of these four different attributes. You multiply them together. This is all yes ones probability, this is all no probability, then you finally get a yes or no based on the prior. You can calculate the posterior. Right? So is that very simple? The base is very simple, right? If you use this ABC set, you just plug in this formula. So there's one minor problem. The minor problem is, what about the probability is 0? You may have the case you find there's no such case in your training data because 0. You say, what's wrong with 0? 0 trump out everything because everything you are doing is time them up. You multiply them up. You get a 1 0, everything is there. So that actually makes your computation a little inaccurate because in principle, if you get a very large training set, this probability may not be 0. But if your training data is small, you get a 0. 0 trump out everything. So all the probability time them together, 0 times anything is 0. Right? So people found that this actually may lead to some inaccurate result just because you have a 0. How they compensate this? They just say, I pretend that there is no 0. How they pretend it? They do a little correction. They play a little trick. They call this one is a Laplacian correction. Okay. This Laplacian correction is pretty straightforward in a sense. If you find this income low at this point for this case is 0, okay, you just assume there's no 0. Okay. How do you assume there's no 0? Suppose you get 1,000 training couples. You assume there's 1, which make it non-zero. Okay. That means you add 1, okay, make it non-zero. But since you add 1, it's not fair to the other classes, right? Because you intentionally add this 1 in. To make the other class also play the fair game, you add everybody 1. You can say, since I know it should not get 0, or get 0, my computation is not accurate. I just add a small number. Okay, what's the small number? Smallest one is 1. So add 1, which makes this one non-zero. I add everybody 1. Every class add. Okay, that probably make it a little fair. Okay. In that sense, you do not have 1,000 couples. You have 1,003 because you have 3 classes. Everybody add 1. And then you can do remaining computation, and I think it should be okay. Right? Actually, this is they call Laplacian correction. We just try to make it non-zero. Okay. Other than that, the 90 base is just very straightforward. You put it into the formula, it works. Okay. So what is a nice thing about the 90 Bayesian? Because it's very easy to implement. If you get this ABC set, you almost get every probability computed already. And you get many reasonably good results. Not too bad to classify. But since you make the assumption, say, class conditional independence, sometimes, especially if you do not first do the attribute checking, you say these are correlated attributes, you don't put them all in. Okay. Then you may make inaccurate. that means you may lose some classical action. Okay. So in practice, for example, you know a lot of things, they do have independence. For example, the age may be independent, may be dependent. Some kind of cancer maybe only the old people may have. You may have family history, you may have bigger chance to get this problem. So people actually know this, you probably can do something. Then if you know the dependency, you will not use naive Bayes. So what do you use? You use Bayesian decision network. Okay, the Bayesian network we are going to discuss, like a conditional probabilistic model, or those more fancier models, you can model it better. Okay. If you know they are not independent, you probably don't want to use this. Okay. So later we are going to discuss this. Why are we getting to this one? We will discuss this Bayesian decision network. That's lead to the very promising, like a probabilistic graphic model. If you go to Stanford or you go to Coursera, the first course you can see is their CEO, I think it's Daphne Kohler. I think that's her. She actually came here to give a talk, but not on her probabilistic graphic model. The book is that thick, all the formulas. But she is a CEO for Coursera, for the course, almost free to everyone in the world. She actually gave a very touching talk, I think it was a few months ago. But she was the authority on probabilistic graphic model. Okay. So we finished this. We are not going to go further. I will spend a few minutes, say 15 minutes, on our midterm exam. Okay, so let's make it full screen mode. Oh, it's even worse because it's smaller. Let's still take this. The first thing is the final exam will cover the first half of the lecture as well. That means the final is really cover the whole semester. Of course, the weight on after midterm material may be a little heavier. For example, I may cover, say, 30 to 40% before the midterm, maybe put, heavier, like a 60 to 70% in the later part. But still, the first midterm, the first half of the semester is non-trivial, still there, okay? So you need to understand it well, but, for a course, you need to understand it better anyway. So we probably look at this. You have any questions, need a detailed discussion, raise your hands, we can discuss it. But I will go over this in the answer set very quickly. The first thing is about naming 5 data visualization methods that can visualize 4-dimensional data. Actually, there are lots of them. Okay, you can, for example, the scatter plot matrices, or many of them, like a dimensionality stacking. Those are the typical ones. As long as you know they can easily visualize 4-dimension or higher, you can put it in. But you put in something obviously is wrong. For example, if you say scatter plot is only good for 2D. Okay, then that's wrong. Otherwise, anything you put it in, which can handle higher dimension. Then the second one is find the maximum difference between any numerical one, the maximum difference in any numerical attribute should be supreme. I think most people know that. I will not explain. Finding 2 text documents, what's the distance measure, it should be cosine. And finding distance between 2 probability distributions should be for the same random variable should be KR divergence. Those are in the definition as well. Okay. I think the last one is a little trickier. Finding a sequence of words that occur much more frequently than expected in the large corpus. Okay. Just give you a simple example. I quite often use, I say, suppose later we are going to discuss one classification method called support vector machine. how do you know these? Suppose you are reading a long article. They have a support vector machine right there. How do you know these support vector machines should be getting together as a phrase? Actually, if you want to find these sequence of words, like support vector machines, 3 words, occur much more frequent than expected. That means, actually, if you randomly thinking about support, we just say support vector, don't say support vector. Just say support vector. Okay. Support vector, you randomly say these two should be getting together to be like a phrase. You say support vector must be something interesting. It's more like United States must be something interesting. Why United States is interesting? Because you find United and States getting together like almost like one word, very frequent. That means much more frequent than expected. How do you judge it? You can think about it. We take United States. Okay. Suppose you say United. You randomly pick a United. You say that's just one word. In the newspaper, maybe United occur, suppose you get 1 million sentences. United occur 1,000 times. Then it's 1/1,000. Suppose states also occur, so 1/1,000. Then United States getting together, if it's random, it's pure random, what's the chance the United States get together? 1/1,000,000, because it's 1/1,000, 1/1,000. If they are random, United States getting together is 1/1,000,000. That means if you read this 1 million sentences in newspaper, you may only find one chance United States getting together. But if you read newspaper, you find United States getting together much more often, much more than one. That means the United States getting together is a phrase. It's a nice phrase. Okay? That's the case. How do you judge it? Why we judge it much more frequent together? Actually, you can use something like a z-score or a significant test, a PMI. Of course, you can use chi-square as well. But usually, the chi-square, you have to calculate all the 4 different probabilities. The z-score is much easier. You just calculate 2, right? 1/1,000, 1/1,000. Getting together, 1/1,000,000. But you check this, you can easily say this by drawing a Bayer curve or drawing a Gaussian. In principle, it should be 1, but now it's like a 100. Okay, it's 10 standard deviation away from the from your distribution. That must be a very nice phrase. That's why you find it in the United States. Right? So actually, we do have some nice research papers how to find phrases automatically without anybody training. It's based on these things, like z-score or PMI or significant test or anything else. You can get it very quickly. That's one of my PhD students that did this. You find all those phrases in almost any language. Finding quality phrases takes almost no time, like a sub-second. Follows through finding all the phrases. That's phrase mining. Actually, this one question actually leads to some very big paper. Okay, very big research stuff. But that's the one. I just wanted people to look at this to figure out what it is. I think most people got the answer. If you write down, chi-square, we still give you answers, even if it's not so nice. If you write down z-score, it should be the best one because it's so simple to compute. Somebody took because originally TA may took your points out. TA sent a reminder everybody if you answer z-score, significant score, PMI, or anything like this, you get your score back. Okay. So this is what's a measure range. I think this is almost in the textbook. I probably should not even spend time on this. This one, supreme distance. Okay, people have 2 answers. One answer is 0 to infinity. You assume it could be anything. I have a given set. I expect you write down something like this, the smallest one, the largest one in any dimension. But it's fine. Any one you'll get it right. You get this one, you get full scale, you get this one, also get it. Okay. I think this key difference is, I think everybody, if you know it, it should be right. I probably do not need to lecture on this. Now come down to this part. this part, I think if you are very clear, you think it's very easy. But some students really stuck on that to get things wrong. Okay? So I probably should say the first thing, this one most people get right. Because you have 10 dimensions. Remember, 10 dimensions, how many cuboids you get is 2 to the power of your number of dimensions. Okay? You assume there's no level. Even you put the level of things there, you only have one level, 1 plus 1 is 2. You still get 2 to the power 10. Okay? No matter which formula you use, you get 2 to the power 10. Okay? Then, how many aggregated closed cells? Okay. Closed, you just think about closed means the support or the number, the count is different. Okay. You just remember this is the most important judgment. Okay. And how many things you get different? This is 1, 1. There's only one chance to get different is you get something like this. A1 star, A3 stars, star A5 or something. This one will happen once, you get 2. That's the only one. Because no matter how high you go, you take all the stars, you still get 2. They are not closed because this is the one, is the first time you get it. Actually, you get it. Remember, the closed one is, no anything, the superset. You still get different one. You still get same. So this one is closed. You will only get 1. Then, how many non-empty aggregate cells? Aggregate cell essentially, originally, okay, you don't think about redundancy. It's each distinct cell, you will generate 2 to the power 10. But if you say you take those initial one, you only count the aggregate one, it's 2 to the power 10 minus 1. So that's why you get a 2 times 2 to the power 10 minus 1. That part is you don't count any collision. Okay. But there are cases like this one. That's why I put this one in the front. Okay. This one actually have 1, 2, 3, 4, 5. You have 5 non-star ones. This one itself will generate 2 to the power 5, ancestors, those cells. But those cells, actually, they all like 2 combined to 1 because the support is 2. 2 combined to 1, you have to minus those overcounted 1. Those overcounted 1 is 2 to the power 5. That's why it minus it. Is that clear? Hopefully. If you still have questions, you come back to my office. I can explain that. And then we say if the minimum support is 2, we want to find all the non-empty aggregate cells. That's essentially is 2 to the power 5. Maybe I should swap this to order. You probably make your life even easier. Because you first get this, you just minus this, you get it. Right? So, but anyway, these two, either order. You get this one right, you should put it in. Right? That's the only time. So, one thing about this, whether it's algebraic measure. Algebraic measure, you can see you get a quantile. Quantile is similar to the median. This quantile is not algebraic, it's holistic. It's like a median, right? You know the median. Median is 50% quantile. Then you get a 25%, 70% quantile. You still have to count the whole data set to get the quantile. So that's why this actually this is similar to the median. It's holistic. Holistic, you add this 2, divide by 2, you still get holistic. Once you get anything holistic, the whole formula. Right? And the standard deviation is yes, right? This quantile is no. And bottom 5, I just say try to get a sum of the bottom 5. Actually, bottom 5 is algebraic. Somebody got confused. Bottom 5 means you get the smallest 5. The smallest 5, every time you pass, you just need to pass this 5 value down to the, for example, you get Illinois bottom 5, Wisconsin bottom 5, Michigan bottom 5. You want to count the whole Midwest bottom 5. You just send these bottom 5 down there. And the final Midwest bottom 5 must be within this bottom 5. Right? So that's why it is very broad. Is that clear? Hopefully. If it's still not clear, we can discuss afterwards. Okay, this bitmap I found while I was checking the student answer. I found somebody got this a little difficult. The problem that day I did not give the lecture. I actually was in Denver for the meeting. I probably did not get a chance to explain this one clearly. Okay. The general philosophy is this. Okay. How many bit vector? Since you have 8 dimensions, everyone has 50 distinct values. Each distinct value, you need a 1 bit vector to map the whole thing. Okay. So you have 8 dimension, each dimension have 50 distinct values. So total you have 8 by 50, you get 400 distinct values. And each distinct value you need a big vector. That's why you need 400. Okay. Then you have 50,000 cells. 50,000 cells means because each cell you need 1 bit to represent it. You get 50,000 cells, so every bit vector must contain these many bits. Okay. That's the reason. That's a bit vector, that's a bit. Okay. So if you're not familiar with this, you can discuss with me. I probably, because I did not teach this, I actually probably did not emphasize this as a midterm question, right? So you need just a little careful to read this. I think hopefully this is not too many points for some people. Okay. So I think the bug or these things should be very straightforward. A bug can do iceberg, but a multi-way array cannot do it. And the shear fragment actually, we did not discuss this in detail, but actually you can do this as well. Okay. And the efficient OLAP, essentially this, for larger one, larger than 50, these two just cannot handle it. So you have to use the multi-way, the shear fragment way to handle it. This one is a little trickier. I probably just need a little explanation. I think the remaining one probably is somewhat straightforward. This one says you got 100 attributes. You get 1 million tuples. Each attribute has 50 distinct values. Then we just say, what is the size of the shear fragments? Shear fragments, remember, the shear fragments, what you count is you have 0D, 1D, 2D, 3D, 4D. That's all the shear fragments you get. 0D, you need only one cell to get it. And for 1D, remember 1D, you have 50 distinct values. You need a 50 thing to hold it. Okay. And that's, but you have 4 dimensions. Each dimension you get you have these values. So you need 4 times 50. Okay. So similar thing, you get 2 dimensions. Each one get 50 square. So you totally have 6 dimensions. You need this. And if you have a 3D, you have 3 ones. You need this one. Okay, that's a number. But I know a lot of students got this one confused because you got this, then you time the last. If you count the base cells, you get 50 times 4. No matter you count or not count, I told the DA you all give them points because some people are thinking they don't count this. The base cell. Some people you count, okay, but you just need that much. And you times 16, you get the total cell. Okay. This one, I expect everybody should get right, but I do not know. Somebody got it wrong. You can think about it. You have 2 instant values. You have 6 inquired values. Total, you have 8. You have 8 inquired and instantiated. You get 8. You have a 4D, the 4 dimension. So in the best case, you still need the 2. Best case, that means all these, the 2 ones cover all your instantiate and the inquired. So you just need the 2 fragments. In the worst case, they're all scattered, so you need 8 fragments. So the best and worst is 1 is 2, 1 is 8. So if you're not quite clear, you can discuss with me. This one about incremental mining, this is the same as you get 2 scans. It's the same as the one we give in the class on the 2 scan. You can do the mining in the main memory. You only need to scan the database twice. That's the same thing. You can think about it. One already done, the other one. So you need to scan the whole thing twice. We don't have time to explain this, but I just say, if you get a question on this, you essentially is, I probably should say this. You get an old database, you already get all the counts, right? You get a new database. The new database, you scan it one, you mine this once, you get all the frequent ones, their count there. But you need to know whether the other one you still need it. You still have to go back to that database to get all the counts add together. You will know whether it's frequent or not. So that one means you mine from the new database, get all the frequent patterns. Then you get that count. You go down to the old database. You scan the old database once. You get this count. Then you can merge the counts. You will get it. So this one, probably, how many people still get confused on this one? If it's a very small number of people, you can just come back to my office. I can explain it because I don't want to spend the whole time for all the students. But if majority is still confused, I can spend time on it. This one, in principle, is you just do it. The quickest way is you just look at it, finding patterns or size or 2 or something. You just try to extend it. So that will be quicker than you construct a tree or do aperture. But you get this, you get all the others. You essentially need to count how many 2s and how many 3s. This one is the tricky most one. Okay, I think a lot of students got stuck in there. Okay, you can see this is the lift formula. This is the cosine formula. I explicitly said that this is a relative support. Relative support means you get this absolute support divided by the whole size of the data. Okay, that means you take this relative support, you expand it into non-relative. This is absolute support count divided by n. Once you put this n out, everything's so obvious. You can see this. Why? You can see the cosine, you divide by n, divide by n. Because you take as a square root, this n becomes 1n. And these 2 n's are cancel each other. So it's nothing to do with your whole transaction size. And this lift, you cannot cancel this n. So this n flip over. Once you get more transactions, including null transactions, this one will explode. Because you get 100 times bigger n, this number will be 100 times bigger. But this one, you get 100 times n, there's nothing changed. So that's the reason this one is null invariant, this one is null variant. Because null is sitting inside your big N. Okay. These are all non-null things. These A, B, A, and B, these are all non-null things. Null things sitting in this N. Once you expand this one from the relative support to absolute support, everything shows up, or N shows up. This N, because the square root is canceled. That's why there's no N anymore. That means this one, no matter how big your number of transactions, if they are all null, this one will not contain it. But this one does contain it, right? This is a little trickier. I expected a lot of people may not be able to do it. But I mean, I actually mentioned this. If you watch my video, I said this one is a very good question. I did not say this one must be in the middle. Okay. But I just want you to think about it. Why? I explicitly mentioned lift and cosine formula so similar. But why is one is invariant, one is variant? It's a very good question. But I said very good question. I did not say it definitely will be in the midterm. Then I just think about it. Anybody will watch the video or go back and think about it. Why? If you go back and think about it, you get 1 point. Right? You get 4 points. So I think that's all things. If you still have problems to understand it, you come back to see me, okay, anytime. Thank you.